also break down validity problems by the kinds of errors or the structure of errors that they represent. Let's directly use let's look at the graphic first. So our measurement can, in that sense, be broken down into 3 parts, and each measurement instrument, you could say, has all 3, but we want a mixture that is a lot of this. The signal, the proper measurement, where we really want to represent, or really do represent, what was the reality relative to the theoretical construct to study the phenomenon. Right? The signal, that's what we want to maximize. But then we have 2 kinds of errors that can occur. Bias, or systematic error, is then error that is pooled in some way, that is not that we can predict where it happens. It may skew the data in a certain direction and suggest a data signal that isn't really there. So this is a big problem, such a systematic error. Whereas we also have so-called noise or random error, which is also components of the measurement that don't represent the signal, so it's not what we really wanted to measure, but the sources of this error are random in the sense that it's not pooled at a specific case or skews the results in a certain direction, but is just random and unpredictable where it occurs. Let's look at an example. For example, we can look at what an IQ test really measures, and this breaks down into this valid part and into the invalid parts. The proper measurement, or the signal, would be the problem-solving capacity of individuals, the mental problem-solving capacity of the individuals. This is what we want to measure, and this pushes our data towards the true value. However, we have this random error here as the first invalid part that we also call noise. And for instance, that may be that certain participants are very nervous, or other participants slept too little, maybe also because they were nervous. And that's something we don't want to measure. But luckily, it's unstructured, unpredictable, and will not repeat or pool at certain units. So we hope that it creates fluctuations around the true value. Of course, it pools in the sense that just this one person is nervous and the problem-solving capacity appears lower than it actually is. But the idea is that whether you are nervous or not, or haven't slept well or not, that this is not something that happens every day to the same person, but it varies. One person is nervous on one day and another person is nervous on the other day, so we can treat this as a random component. If we don't want to analyze or want to pay a lot of attention to the results of a very specific individual, we just want like the general distribution of IQ test scores in a certain population, then this is not a big problem that some of them were nervous. Right? Some of them are always nervous, but we don't know which, and that doesn't really matter. However, there's also this systematic error that can cause systematic bias, and what might cause such a systematic error in IQ test measures, that would be education, training, or exam anxiety. We really don't want to measure exam anxiety, for instance, or the amount of education a person has received. And unfortunately, this is structured, predictable, and associated with certain units or stable characteristics such that errors repeat and or pool. So the nervousness is one thing, but if the nervousness reflects exam anxiety, then this pools in the individual person, and that person will have predictably lower scores. and we may have one sample that has a higher education than others, and they have systematically higher scores, even if their problem-solving capacity is basically the same. So the problem here is that it skews the measurement away from the true value in a particular direction, which is a big problem. So to summarize, the systematic error is the much more serious thing and what we want to minimize as much as possible, whereas random errors just introduce noise and imprecision into our data. So that should also be avoided, but not at as high costs as systematic error should be avoided. So random error is a problem, but not as serious as the systematic error. But nevertheless, the important thing is to maximize the signal you get out of the noise at as minimal a bias as possible.